In this lesson, we're going to learn how to solve inequalities algebraically and graphically. And we're going to start with the simplest inequalities, which is just linear inequalities. So we're not going to see a degree that's higher than 1. So first of all, what is an inequality? Well, it's like an equation, but instead of an equal sign, we have an inequality sign. So instead of saying these two expressions are equal to each other, one is less than the other. Sometimes we can have an equal to sign here, a less than an equal to sign. So the expressions can be equal to each other, but are not restricted to that. Or sometimes they're not equal to each other at all, like in this case here. So let's take a look at this case. What does this even mean? 4x minus 2 is less than 10. This is asking us to solve this inequality. So when is 4x minus 2 less than 10? Specifically, for what x values will 4x minus 2 be less than 10? Well, what is 4x minus 2 as an equation? Well, that's just a linear equation. That's just a line with a slope of 4 and a y-intercept negative 2. And we can think of this as a line as well, y equals 10. So let's graph this using Desmos and to help us better understand what this is asking. So here we have our two equations. Our first equation is y equals 4x minus 2. That's that line with the y-intercept of negative 2 and slope of 4. And then we have the line y equals 10. And remember what this question is asking us, or what this inequality is asking us. When is this line going to be less than 10? So when is this red line here, when are its y values going to be less than 10? Well, when are they equal? We can see at the point of intersection of these two lines are at the point 3, 10. Now we're only interested in the x value here. So these two functions are going to be exactly equal at the x value of 3. When is the 4x minus 2, the first function, going to be less than the second one? Well, everything before 3. So when the x values are less than 3, the red function 4x minus 2 will be less than 10. So here is our solution. Our solution is highlighted. For all x values that are less than 3, our function 4x minus 2 is going to be less than 10. So now that we figured out what this looks like graphically, can we get the exact same solution algebraically? Before we're able to solve that inequality algebraically, we need to know a couple things about working with inequalities. So let's start off with an inequality we can all agree on. So let's say negative 2 is less than 1. Do we agree with this? Well, of course. Negative 2 is here on the number line. 1 is here on the number line. This has to be true. So let's start with this true statement and let's manipulate it and see how these inequalities would work. So why don't we try adding a number to it? So if we put negative 2 and let's add 3. And we'll add 3, of course, to both sides. So we have 1 and then plus 3. Is this still true? So negative 2 plus 3, that's going to be 1. And 1 plus 3 is 4. Is 1 less than 4? Yeah, that's fine. So adding things to inequalities doesn't seem to be a problem. Same as subtracting. Let's try another subtracting. So let's try to subtract 5, let's say. And we'll subtract 5 from the other side. Are these things still true? So we have negative 2 minus 5, that's negative 7. On this side I have 1 minus 5, negative 4. Is negative 7 less than negative 4? Yes. So adding and subtracting any number to inequalities, both sides of the inequalities, doesn't change the fact that this inequality remains true. Let's try multiplying and dividing. So why don't we try multiplying the entire equation by positive 2. So I'm going to start with negative 2. I'm going to multiply it by 2. And I'm going to leave my less than sign, and we have 1. I'm going to multiply it by 2. Is this still true? Well, negative 2 times 2 is negative 4. 1 times 2 is 2. Is negative 4 less than 2? Yes, it is. So there's no problems here. So let's try dividing. So let's try dividing everything by 2. So I'm going to do negative 2 and then divide by 2 and see what happens. And then on the left side, I'm also going to divide by 2. Is this still true? Negative 2 divided by 2 is negative 1. 1 divided by 2 is 0.5. Is negative 1 less than 0.5? Yes. So far, inequalities seem to be working exactly the same as equations. Here's where the problem is. We added and subtracted by positive numbers and negative numbers. Let's try multiplying and dividing by negative numbers now. So I'm going to try multiplying by negative 2 instead. So I'm going to take negative 2 and multiply it by negative 2. There we go. And let's do the same on the left side. So we're going to start with 1 and multiply it by negative 2. Now does this inequality remain true? Negative 2 times negative 2 is positive 4, and 1 times negative 2 is negative 2. So is positive 4 less than negative 2? No. So something has happened here. So let's circle this case. Let's try dividing by a negative now. So let's try dividing by negative 2. So I'm going to start with negative 2. I'm going to divide by negative 2. And on the left side we've got, on the right side we've got 1. And let's also divide that by negative 2. Does this one have the same problem? Well, negative 2 divided by negative 2 is positive 1. Less than 1 divided by negative 2 is negative 0.5. Is 1 less than negative 0.5? No, 1 is greater than negative 0.5. So this is not true. So both times when we multiplied by a negative or when we divided by a negative, it made this statement not true. But what could we do with this statement to make it true? Can we make a slight change to make this inequality still true? Negative 2 times negative 2 is positive 4. It's not less than negative 2. It's greater than negative 2. So what if we were to just switch this sign in the middle to a greater than sign? Just like this. Would this be true? So this would say now positive 4 is greater than negative 2. Now the equation would be true, or the inequality would be true. How about this guy? Negative 2 divided by negative 2 is positive 1. That's not less than negative 0.5. It's greater than 0.5. So if we change this to a greater than sign, is this inequality now true? Now it says positive 1 is greater than negative 0.5, and that's definitely true. So we could try this for case after case after case, and we're going to still notice the exact same pattern, which is that if we divide or multiply by a negative number and we keep the sign the same, our inequality is no longer going to be true. If we multiply or divide by a negative number at any time when we're solving inequalities, we have to switch the sign. If it had a less than sign, we've got to change it to a greater than sign. And if it had a greater than sign, we've got to change it to a less than sign. So now we've got everything we need to solve this guy algebraically. We know what the solution should be. According to Desmos, we know that the answer should be x has to be less than 3 in order for this to be true. Let's make sure we can get that same exact answer algebraically. So let's just rewrite the equation. Remember, we can treat this guy exactly like we would treat an equal sign. We can add to both sides, we can subtract to both sides, we can multiply, divide to both sides, but just we have to remember if we multiply or divide by a negative number, we got to switch this sign. So we need to figure out for what values of x is this true. So just like in a regular equation, we got to isolate for x. The first thing we're going to do is get rid of that minus 2 by adding 2 on both sides, and we'll be left with 4x is less than 12, and then we've got to divide by 4. Notice that when we tried those other examples, dividing by a positive number, there was no problem. It's just when we divide by a negative number, there's a problem. So we're going to keep that less than sign, and then we have 3, and which is the exact solution that we got from Desmos. We can represent our solution on a number line like so, just indicating where 3 is. We know that x has to be less than 3. It cannot be equal to 3, note, because this is just asking when it's going to be less than 10, not equal to 10. Otherwise, we would have an equal to sign here. So if our solution does not include 3, we're going to put an open dot at 3. That means that that solution is not included, and everything that is less than 3 is included. So that's another way to represent our solution. Let's try another example. So this one is asking, when is this function going to be greater than or equal to this function? So what is this function? This is just a linear equation, and so is this one. So we can expand this quickly just to have a better idea of what this is going to look like. So this is 20 minus 12x. And when is that greater than negative 6x minus 16? So again, we can just see these as two linear functions. So this is a function with a slope of negative 12 and a y-intercept of 20, and this one has a slope of negative 6 and a y-intercept of negative 16. Let's take a look at what this looks like graphically, and we'll solve it algebraically. So here we've got the two linear functions graphed. So in red we have our first function, 20 minus 12x, or y equals 20 minus 12x, and in blue we have our second function, negative 6x minus 16. And the first question we want to know is, when are they actually equal to each other? So it looks like they're equal to each other when x is equal to 6. So should our solution be x is less than 6 or x is greater than 6? Remember what it's asking. It's asking, when is this red function, this first guy here, greater than this function? When are the y values of the red function greater than the blue function? So if we just try something that's greater than 6, for example, let's try whatever this number is here, which y value is going to be greater? Well, if I bring down an x value from here, we're going to hit the blue line before the red line, which means that the blue y value is going to be greater than the red y value. So that is not what we're looking for. We're looking for when is red greater than blue. On the other side here, if I were to plug in this x value, I'm going to hit the blue line first, which means the red line's above it. So the red y values will be greater than the blue y values, and that's exactly what we're looking for. This is our red function, here's our blue function. We're looking for when these y values are bigger than those guys. So for all values that are less than negative 6, this is going to be true. And for all values greater than negative 6, the opposite will be true. So if we let Desmos show us the story, we can see that our prediction is right. For all y values that are less than negative 6, the y values of this red function will be greater than this function. So let's try to solve that algebraically now. So we're going to do it in the exact same way that we did in the previous example. Let's collect the x values, and we're going to collect the constant terms. So I'm going to move this 20 on this side. I'm going to move this 6x on this side. So we're going to have negative 12x plus 6x is greater than or equal to negative 16 minus 20. And then we have negative 6x on this side. We've got negative 36 on this side. We can divide by negative 6 and divide by negative 6. Do you remember what we need to do now? From our first example that we did, we know when we divide by negative numbers, this is not true anymore. The opposite is true. And so if we do this, do not forget on the next step, do not forget to change that sign from a greater than sign to a less than sign. So we have x is less than or equal to positive 6. And that was our solution. We proved it graphically that this is only true. This function is greater than or equal to this function only when x is less than or equal to 6. So here's our final solution. We can show it on a number line. We have this as our 6. We know the solution is going to include 6, so I'm going to have a closed dot and everything that's less than it.